I want to start with 2 or 3 slides of general background where we currently stand. And starting with a little bit of history. So this is an article from 1958, which appeared in the New York Times, here on the left-hand side. A small, insignificant article which says, "New Navy device learns by doing." So this was reporting on a press conference where Frank Rosenblatt, this guy over here, demonstrated a new machine, or reported a new machine. On this new machine that he called a Perceptron, and he showed that it could learn from experience. And he predicted that, or he said it was the first machine to think like the human brain, learn from mistakes, and he predicted that later perceptrons will be able to recognize people, call out their names, and instantly translate speech into other languages or into writing in other languages. So this was the birth of neural networks, the birth of connectionisms, so the attempt to build synthetic brains. Now, around the same time, there was another revolutionary development underway. And this development was that people understood that computers could do more than just compute with numbers. So the initial computers, as you probably know, were actually humans, at that time mostly women, doing calculations by hand. Then people moved to mechanical, electronic computers. And around that time, then they understood that you can do more than just numbers, you can process symbols. And this was quite a profound insight, and it was really what gave birth to the field of computer science the way we know it nowadays. And the success of this insight was so impressive, so people developed programming languages, etc. The success was so impressive that effectively funding for connectionism, which was kind of the competing paradigm, actually stopped. So people believed that the manipulation of symbols was in programs written by humans was all that's necessary to generate intelligence. And so this is a picture of Herb Simon, one of the founding fathers of that field, also one of the founding fathers of causality, as it turns out. He said in 1956 that within 20 years, machines will be capable of doing any work a man or a human can do. So this field, they then set out to automate the work that men around that time were presumably doing, or that they considered worthy things for men to do, things like automatic theorem proving, computer chess, etc. Made some initial progress, but then it turned out that the problems that actually appeared simple, that maybe even were too simple for intellectual men like themselves, so most of the things that animals could do, they turned out to be hard. And this is sometimes called Moravec's paradox. Now this has changed now. It turns out we can now now we're moving back to data-driven methods, moving back to connectionism, pattern recognition. We can now solve, or at least we think we can solve, some problems that were considered easy but turned out to be hard. According to Moravec's paradox, we think now we can solve some of these problems. So we can finally solve the easy problems, but the question is, do we really solve them, and how do we solve them? And discussing this a little bit leads to motivation for why we should be interested in causality. So we often hear that in object recognition we have now reached, or maybe even surpassed, the human accuracy level. So this is a nice slide that I took from Pietro Perona, where did I tell?
Since clearly there's something not working right, instead take a 15 minutes break, go to your tea time, and then you take a tea break or something right now, and then we try to start that. Otherwise it will just be...
We take a quick break now.
Instead of break, and then where's the camera people? Please sort this out.
So we start again 10 minutes past 9?
Or quarter past maybe.
Or quarter past 9. Oh, it's coming back. So what okay, next time it fails, we take a break. Okay. Actually, I think they're showing something from the back because I see something else here. But okay. Okay, so then if you move to the next slide. Yes, keep going. Yes, okay. Okay, it's a little distorted, but I think you can do the transformations in your head. These are compressed cows. So we have these impressive systems that can recognize objects, can recognize animals. This has been really quite dramatic progress. So we train a system on a huge set of labeled images, and then by some measure of success, we achieve human-level performance. So in these 3 images, we just recognized all the cows. So now we know it's not the connection from here to the back, but the connection from the back to here. Okay, so we can recognize these cows in these 3 images. But if you go to the next slide, I look at some other images here where there's also clearly cows on the images, although maybe there might be slightly different species of cows, but more importantly, cows in strange contexts. Then we don't recognize them anymore. So that's kind of surprising, and one way to interpret this is to say that if there are things in a test image, such in this case the beach or the sea, that are negatively correlated with the presence of cows in the training set, then the system may not recognize cows anymore, and the reason is that machine learning is based on statistical dependencies, and if there's a strong statistical dependence between the presence of a cow and the background in the training set, then the machine learning system is going to exploit this dependence. Machine learning doesn't care about causality or what is directly causally connected to the presence of a cow in an image. So we are bothered by this. Our own object recognition system does recognize these cows, and this somehow points to the idea that probably our own systems not only are more robust, but maybe also use causality in a different way from the standard machine learning IID systems. IID standing for independent identically distributed. So the current machine learning paradigm is very much about we have one fixed data source, then we can draw data from this source. We can ideally draw unlimited amounts of data from this source, and the source doesn't change as we draw the data. That's what everything's optimized for. That's how we construct the data sets. That's how we evaluate the systems. That's how the theory is developed. There's another example where this is maybe even more extreme. If you go to the next slide, which is about so the machine learning system. Since please move one slide. Sorry, yeah, this one. So machine learning systems are highly optimized to a given data set, as I mentioned before, which also implies that they are not robust with respect to even small violations of the IID assumption. So if we add just a little bit of malicious noise to a test image, actually imperceptible to a human in this case, then the system may suddenly recognize this peak as an airliner. Yeah, so let's move to the next slide. Okay, so this is another way of motivating or discussing why the IID assumption is not innocuous. And this is with a shopping example. So in this case, we are shopping for a laptop rucksack, and then the shop recommends that we should buy a laptop to go along with the rucksack. Now, this is of course slightly funny, because intuitively we would say that buying the laptop, buying or owning or buying a laptop could be causal for wanting to buy the rucksack, but it doesn't feel like there's a causality or a direct causality the other way around. So having the laptop makes us want to have the rucksack, but not the other way around. Okay, this is interesting. Oh, okay, that's myself. I'm now getting caught in some kind of infinite loop. Now, interesting, if you think about it from the statistical point of view, so if I tell you that someone put a laptop rucksack or has a laptop rucksack in their shopping cart, it probably reduces my uncertainty about whether there's also a laptop in the shopping cart. And the same is true the other way around. And it reduces the uncertainty by the same amount, because that's called the mutual information, and it's a symmetric notion. So the cause contains information about the effect, and the effect contains the same amount of information about the cause. The cause contains information about the effect because it controls the effect, whereas the effect contains information about the cause because it carries a footprint of the cause. But somehow the reason why they contain information about each other is quite different in the two cases. And this kind of symmetry this asymmetry is lost in standard statistical analysis or machine learning. So let's move to the next slide. So just a few more examples to give you an idea where the problems of causality come up. So this was from a large study looking at mortality in a huge group of people and how it's associated with coffee drinking. And in this study, the results, if you click once, we might see them. It's probably a little bit too small, but so they say that in age-adjusted models, the risk of death was increased among coffee drinkers. But then there are some other things that coffee drinkers are also likely to do. So coffee drinkers were also more likely to smoke. And if you also adjust for whether they smoke or not, then suddenly it's positive to drink coffee. You live longer if you drink coffee. So it seems like it's a strange thing. So does coffee make you live longer or shorter? And in the end, it depends on this, what they call adjustment. So we'll get back to this later. So it looks like you have a big data set, and in the end, you still can't say what's the causality here. And statistics is full of these problems. And they even have these big tables, if you move to the next slide, of which different habits have which kind of effect depending on coffee. So if it's to the left, then the coffee helps. If it's to the right, then coffee is negative. And you can, I'm not going to go into details, but it's, I think one of the interesting things I thought was, so mostly you can get the same benefit from decaf, only that the positive effect on whether you die in an accident of decaf is weaker than of caffeinated coffee. So if you are driving at night, drink coffee with caffeine. So let's go to the next slide. So this was also an interesting study. I'm sorry, this is in German, but you don't have to read this. This was a famous study in Germany where they looked at the incidence of leukemia in the vicinity of nuclear power plants. And they found that certain types of cancer, or at least I think it was childhood leukemia, was more common the closer you get to a nuclear power plant. And in the end, in the study, they say, what did they say? They said something like, we don't know, we cannot argue there's a causality because we don't know what could be the causality. So it could be that we have left out some factors. And so we recently looked at this paper, tried to understand it in more detail and data sets. And it's very difficult to control for all the variables that you should be controlling for. So, for instance, it could be that the families that live closer to nuclear power plants also have some other systematic differences. It could be that they are poorer, maybe the expensive houses are not close to power plants. And then a lot of factors around diseases are related to wealth, as you probably know. So your risk of dying from various diseases goes down as you get richer. So there are all these problems about that. And then finally, the last one, please move one slide. Next slide, please. So the last one is kind of a funny dependence that you may have heard of. This is between the frequency of storks in various European countries and the human birth rate. And in this case also you find quite a strong correlation between the two quantities. So there's this funny paper in the journal called Teaching Statistics. And in this case, of course, we would not think that this is a causal or somehow a direct causal connection. So we would not. So suppose you are running a country in Europe, you wouldn't say you can increase the human birth rate by having more storks in your country. So let's move to the next slide. So all this is just hammering on this point that you probably all heard many times, that correlation does not, sometimes people say correlation tells us nothing about causality. Now, so there's a few things are problematic with this. First of all, of course, as you probably know, we should not really talk about correlation, we should talk about dependence, because correlation is just one form of dependence, it's just a first order sort of linear dependence. Okay, let's put that aside. Second point is it's a little bit too strong to say that correlation tells us nothing about causality, so it turns out it tells us something, and the first person who understood this was Reichenbach, and please next slide, who was a very interesting guy, a philosopher by training. He did his PhD on the foundations of probability theory. He had big trouble finding a PhD advisor who would give him a PhD for this work, but he eventually managed, and then he was hired into a physics department by Einstein and Planck and von Laue into a physics department in Berlin. And he had to leave Germany in 1938. He went to Turkey and subsequently later to America, where he started the philosophy school. He was the PhD advisor of Hilary Putnam, for instance. And he wrote this book, which is called The Direction of Time. And in this book, he thinks about the connections between dependence or correlation and causality. And he postulated this principle that says that if you find two quantities in the world that are dependent, so think of the storks and the human birth rate, then there must be some quantity z that causally influences both of them, so there's no statistic dependence without causation. And this z can be chosen such that it screens x and y from each other, in the sense that it explains all the dependence between x and y. So there's nothing that's not explained by z, which mathematically means that conditioned on z, x and y become independent. So if you click once, so this means that so in the generic case, z causes x and y. So in this talk, arrows mean causation. And now, of course, as a special case, z could coincide with either x or y. So we get one of these pictures on the right. If you please click once. So that means, in our case, with the storks and the babies, it could be that the storks bring the babies, it could be that the babies attract the storks with their loud shouting, or it could be that there's something else that causes both of these quantities, such as economic development, environmental pollution. I don't know, you can think of lots of different possible z's, and this is sometimes called a confounder. So this is a quantity that we often don't see, or we don't know that this is the one that we should be looking at, and it influences our two quantities of interest. Please click once. Now the interesting thing and the motivation for this talk is that in the end, all these three cases, they lead to the same observable consequences. So any observational distribution, so any set of observations of x and y that we might imagine can be explained by any of these three models. So that makes the problem difficult. Okay, please, next slide. So this is just a brief list of notation. I assume at some point we'll have the slides on the webpage or something, so you can always go back later. But so we'll have events A, B. I think I only need this at the beginning. Then random variables will be x, y, z, or sometimes xi, xj. Then, as you probably know, so random variables are, so events are subsets of your sort of universe, where the observations come from. Random variables are functions defined on that set. So the idea is we have a random experiment, it generates something, and then a random variable is a function that assigns a number or a vector to whatever has been randomly generated. I mean, we often directly think of the random variables as the outcome of the experiment. If you want, you can do that as well. probability measure, then we have a particular type of probability measure is what's called the distribution of a random variable. That's a probability measure on the reals or on a Rn, or more precisely on a sigma algebra defined there. For lowercase p we use for density, and we'll assume there's always a density, so we keep things simple. So we don't have to talk about measures themselves, but we talk about their densities. If we want to talk specifically about the density of a random variable x, then we sometimes use x as a subscript, or we just put it into the argument, which is a little bit confusing. So I hope, well, I was going to say I hope there are no mathematicians in the room, but that's not a nice thing to say. And actually, I'm also a mathematician by training. So I hope the mathematicians who are in the room will be able to fill in all the formal details in their head, and I'm trying to find some kind of compromise here that speaks to both the mathematicians without annoying them too much, and to the people who are less into measure theory and sigma algebras, etc. Sometimes we use the lowercase, so p of lowercase x means density of px evaluated at x. And also just briefly to remind you, there's this thing called the chain rule. You can look it up on Wikipedia, which follows from the definition of conditional probability, and you also need this kind of thing. So it's a way to decompose a joint density over a set of random variables into, in the end, a product of conditionals, where the first conditional conditions and all those, and then the next one is the distribution. So if you look at this formula, so if you first decompose it like that, this is now the distribution xn minus 1 to x1, and then you use the same thing again, and then by induction you get a product of n terms. So then that's one possible way to express a joint distribution as a product of conditionals. And now it turns out in causality there's a different factorization of a joint distribution that we like much more, because it corresponds to the causal structure of the world, and I'll get back to this one. So this is just a general mathematical statement, and I will always assume, whenever it's necessary to assume, I will implicitly assume that these things are non-zero, because sometimes you have to divide by something. So next slide, please. Independence. You probably have heard of independence. Usually in mathematics, the way it's defined is one first defines it for events. So there's a way of defining when two events are independent in terms of the probability measure. And then, first of all for two events, but then if we have n events, the definition is like this, so that it has to be, sort of the generalization of this formula up there has to hold for any possible subset of these events. So you don't have to remember this in details, but it's, one thing to remember is that if you have pairwise independence for any two events, that does not in general imply joint independence of all these events. And if we go to the next slide, we have the same for random variables. So two random variables, remember this notation with this sort of orthogonality symbol, are independent, so I can't use my mouse pointer. I wonder if there's a laser pointer that might be useful to point, but it's not urgent, maybe after the break. So two events are independent if a certain sufficiently large set of events are independent. So these events are just measuring whether a random variable is bounded by A or B. And if this is too complex, then you just remember this one. If we have densities, then two random variables are independent if and only if their densities, the joint density factorizes into the product of the two marginal densities. So pxy is p of x times p of y. Now, one thing that's interesting about independence is that, first of all, if we have two independent random variables, x and y, then the expectation of the product will factorize into two expectations. So that's a non-trivial statement. And also in this case, the covariance between x and y will turn out to be 0. Now the converse is not true. So if the covariance is 0, it does not imply that x and y are independent. And this, I mentioned this already before. The covariance is kind of the first order of dependence. So if it's 0, it just means the first order vanishes. But there's an interesting generalization, and I think we might get to this because that connects to kernel methods also, and I think maybe Arthur Gretton will talk about this in his talk. So it turns out if you look at not the covariance of x and y, but the covariance of f of x and g of y, where you allow sort of arbitrary functions or functions from a very large class, so nonlinear functions. So first of all, if x and y are independent, then also f of x and g of y. So by applying a fixed function that hasn't seen the data, you cannot create dependence. So this covariance between f of x and g and y will also vanish if x and y are independent. But it turns out, so that's a much richer statement if this covariance vanishes for many functions f and g, and it turns out if we start from this, we say that we require this to be true for a large class of functions, then it turns out that this implies independence. So this then effectively this becomes an equivalent characterization of independence. So two random variables are independent if their covariance vanishes even after arbitrarily nonlinear transformations of these variables. Next slide, please. So conditional independence is also something that's used a lot in causality and in graphical models. So two random variables are called conditionally independent, and this is the notation. So x and y independent conditioned on z, or conditional on z. And there are different ways of writing this. Sometimes we put parentheses, sometimes maybe they're dropped. And on the right-hand side, you see the subscript p, which indicates that this is a property of the joint distribution of x, y, z. So conditional independence, and this time we directly define it like this, holds true if and only if this factorization is correct. And there's a little detail here. Maybe at this point, just remember that it's not the same thing as independence. So it's possible to find random variables which are conditionally independent given a variable z, but unconditionally dependent and vice versa. Okay, so this is some basics. Now let's try to get more into causality and get some intuition for what's possible and what kind of assumptions should we need. I already said it's a hard problem that fundamentally cannot be solved based on observations alone. Okay, so here we have a data set, a two-dimensional data set, so two observables. One is altitude of a place. In fact, these are actually, turns out these are places in Germany. So we have a number of weather stations in Germany. They have different altitudes. And the other observation, this axis here, is the average annual temperature. So for each weather station, you measure how high they are and how warm they are. And as you can see, the higher you go, the colder the place gets on average. And I think we all have some ideas why this is true. You can see that most places in Germany are below 1,000 meters in altitude. And the temperature, I think you cannot read, but I think up there is the average temperature 10 degrees. So this is day and night the whole year. And down here is -5 degrees. And now we could ask ourselves what has generated this set of dependencies. If you think back of the Reichenbach picture. And in this case, let's assume it's either T causing A, so temperature causing altitude, or altitude causing temperature. Let's assume there's no confounder for simplicity. So we'll have to decide between these two simple causal graphs here. So this is the one, this is the other one. Well, maybe we can first ask for some guesses. Yeah. So who thinks that temperature causes altitude? Okay. Maybe I should have asked the other one first. Who thinks that altitude? Hot air balloon. Yeah, that's a good example. Yeah. So if we change the distribution, things could be different. But in this case, with the stationary weather stations, who thinks that altitude causes temperature? And causes in the sense, yes, so that's good. A lot of people causes in the sense of having a direct causal influence. Doesn't have to be the only one, so reality, of course, is more complicated. But it seems like people believe that this is a more plausible causal structure. And so before I told you about this chain rule, so we can decompose the joint distribution of P and A for A and T two possible ways. This one or this one. I think I'm blocking the view. I don't know. Maybe one of the participants has a laser pointer here that I could borrow for a while. No? Okay. Oh, I see one. You are our hero. Thank you. That's a beautiful one. No. Okay, I can see it. I don't know if you can see it. Yeah, okay, so if I move here. Okay, so we have the product rule, or the chain rule. We can decompose this either like this or like this. Now we all said we think this is more plausible. So that means we decompose it into a distribution or a density over altitudes. And then this conditional of temperature given altitude, and we somehow think, maybe if we now think about why do we find this plausible, then maybe well, actually, let me get this to this on the next slide. Please move one slide on. There are multiple ways of how we could convince ourselves that this is true. Now, of course, in a way, the gold standard would be an intervention. So intervention, so maybe now we're coming back to the hot air balloon, but no. But intervention in this setting would be we have to intervene. So if we want to check if A is the cause, we would have to make an intervention on altitudes. That means we have to raise the weather stations or raise the cities where they are built without changing anything else. And maybe if we were able to do that, so if we lift the weather stations, then we would indeed find that the average annual temperature changes. But of course, it's an intervention that would be very expensive to do, and it would take a long time. And most of you said already hypothesized that A is the cause without performing this intervention. So maybe what you did is some kind of hypothetical intervention in your head. So you imagine what would happen if I were to change the altitude. And maybe what you were thinking, or I like to think what you were thinking is the following. You still expect that the temperature changes because you think of a physical mechanism in this decomposition that I showed on the last slide, P of T given A, which is independent of P of A. So no matter if you intervene on the input on the altitude, you would still think there's a physical mechanism in place that, given an altitude, produces an average annual temperature. And maybe this mechanism has something to do with, I don't know, with the wind, with the air pressure, depending on the altitude, etc. With lots of details that we maybe don't all remember from school, but we believe there is this mechanism, and this mechanism doesn't care about what altitudes you feed in. So as you intervene here, you're not changing this thing over here. So there's a certain implicit assumption of the independence there, and maybe it also has this aspect of invariance, because we would probably also expect that this mechanism is, since it's independent of the altitudes that you put in, it will be invariant, for instance, across different countries in a similar climate zone. So if we did this kind of data set in Switzerland and then we moved to Austria, we would assume that maybe the distributions of altitudes might be slightly different. Maybe, I don't know, there are cultural reasons why the Swiss built their houses higher than the Austrians or whatever. But this mechanism, we would think, should be invariant across these different countries. So please move to the next slide. So there are different aspects. And actually, if you look at the literature in causality and the history, they keep coming up in various ways. And we like to think of them or unify them in this principle of independence of mechanisms, because in a way the input distribution is also a mechanism. So this decomposition of a two variable distribution into a conditional and a marginal is just a special case of the n variable thing, where you decompose a joint distribution of n variables into n conditionals. A marginal is a special case of a conditional, and if you want the input density is just the way you prepare the system. So it's also a mechanism. So let's say in general we have independence of mechanisms, and this has various implications. And I just talked about this aspect. So it has the aspect that if you write down the correct decomposition of a joint distribution into mechanisms, then these individual components will be autonomous. There will be a certain type of modularity. There will be invariance, so sometimes components will transfer from one domain to the next one. And also the decomposition is such that you can actually intervene on components separately, so that maybe that becomes clearer later if we have higher dimensional cases. Now there's a second interesting implication, which is that these different components in the joint distribution should also be such that knowing one of them doesn't tell you something about the other one. So that's also a form of independence. It's a form of informational independence that I'll get back to later, probably tomorrow, I assume. There's a third implication that will also come up later, and this is so kind of a more trivial implication than these two, but related to it, and it can be in some sense viewed as a special case, and that's an independence of noise terms, which then implies certain conditional independence structures. And only this one is what's traditionally being used in causal inference. So let's move to the next slide. Just a very brief, a few notes on history. So the founding fathers of this field called structural equation modeling, which were actually in economics, they thought a lot about these issues. They thought they were basically driven by this problem. You have several quantities. Should you regress A on B or regress B on A? And when can you interpret the regression causal? So which relations between variables? We often model relations between variables using statistical methods. Which relations are structural in the sense that they capture some structure of the system, and not just a formal mathematical regression between two variables. And they already understood it has to do something with invariance. Herb Simon, that I mentioned before, one of the founding fathers of artificial intelligence, already proposed to use invariance as a criterion to find the correct causal ordering by saying the causal structure is the one that's invariant under the right kind of interventions. And of course, as all the people founding the field up to Pearl also have thought about this kind of issues. I think maybe the one thing that we've added here is that this informational independence, so that the one, not only changing one doesn't influence the other one, but also knowing one of the conditionals doesn't give you knowledge about the other conditionals. Maybe that's a new aspect, which is also sometimes useful for inference, and we formalize that aspect. Please move to the next slide. Okay, so now we get to structural equation models. Yes. So let me move to this side so my neck doesn't get stuck in the one orientation. So let's assume, for simplicity, there's some work on that have also circular causal structures, or that deals with circular causal structures. But in my lectures, I will always assume we don't have circular structures, so it's an acyclic graph. So we assume we have an acyclic graph. We have a directed graph, so all the arrows, all the connections have arrows. with vertices x1 through xn. So these are our observables. We now assume they are placed on a graph with arrows. And the graph, the semantics is such that the vertices will be observables and the arrows will represent direct causation. So that's one way we can write down a causal structure. And so this now only tells us what causes what. It doesn't yet tell us how it causes it. So the how will be modeled by functions. So on each node we will have a function. It could be a different one on each node. And the function depends on its parents. So for instance, the function for this one depends on the red ones. So a function depends on the values of its parents, PA in short. And it also, so far this is all deterministic, right? This is the deterministic functions. These are the values that the parents take. But in addition, here we have a noise variable, the UI, where the shorthand U comes from unexplained. So sometimes people call them noise, sometimes they call them exogenous variables, sometimes unexplained variables. So these are things that we haven't, that we're not taking into account by, not explicitly by modeling. So we leave it as uncertain. And also this is the only source of randomness in this model. And importantly, we will assume that these random variables, these UI, are jointly independent. Okay, so we have some sources of randomness. We assume they are jointly independent. This is connected to the Reichenbach principle. Remember, the Reichenbach principle was saying that if we have two quantities that are dependent, then the dependence must be caused by another quantity that we haven't measured that influences both of them. So one way to justify this could be to say, well, if there were two noise variables, so let's say if the noise variable this one and the noise variable this one were actually dependent, then we should really be modeling a bigger graph where we have some quantity that causally influences both of these things. So assuming these noises are independent is a form of an assumption about what people call causal sufficiency. So our model is large enough that it makes sense to analyze it. And this thing with the graph is also encoded in which are these inputs, is called a nonlinear structural equation model or a structural causal model. Okay, so this is the basic model. Next slide, please. Yeah, so I've already briefly talked about Reichenbach's principle. So in a way, you could say this is just a slight generalization or a sensible generalization of Reichenbach's principle, and it also satisfies Reichenbach's principle. Because first of all, if we take functions of independent variables, they are still independent. So dependence in this model from the last slide can only arise in vertices that depend at least partly on the same noise terms. And secondly, if we condition on these noise terms, the variables become independent. And the second thing I already just mentioned on the last slide. So please, next slide. Okay, so now we have this model. Suppose we have specified the distributions of these independent noise terms. So we've specified a factorizing joint distribution of independent noise variables. Now we can, these distributions of the noise variables now imply a joint distribution over all the observables xi, simply by substituting the noise terms. And since there are no loops, as we continue to substitute, eventually, just by applying these functions here, we will get all the distributions of the xi. And if you want, you could even substitute functions into each other and eventually reduce each variable to a function of noise terms, where in the end the variable xi will depend exactly on those noise terms that are upstream from xi. Anyway, so the detail here doesn't matter at this point, but in the end, due to the randomness of the UI, each xi will be a random variable in its own right, and there will be typically a non-trivial joint distribution over all random variables. So, and it's interesting to think about, the noises, so on each node we have a noise variable that we haven't drawn that feeds into the node and that makes it random. So these noises are independent, but now as we let these noises propagate through the graph, because in the end, for instance, this variable will be influenced by its own noise term, but since it's also influenced by its parents, and these parents are influenced by other noise terms, in the end, this node will be influenced by more than just its own noise term. So in the end, according to the topology of this graph, different nodes will depend on different noise terms, and then they will also, I think you can imagine there's some non-trivial dependence structure will come up, because two variables might share some of the noise terms but not other noise terms, and exactly which ones they share depends on the connectivity upstream, etc. So in the dependence structure at the end between these random variables, you'll have a footprint of the topology of this graph. And that's one of the ideas of causal inference, that if you can then measure conditional independencies, it will tell you something about the graph. Anyway, we'll get back to that later. But each xi is a random variable. We get a joint distribution. This joint distribution is called the observational distribution. We haven't intervened, we haven't changed anything. So it's one particular distribution that's implied by specifying one distribution over noise variables. And this is also what's called a directed graphical model. So we have maybe derived it in a slightly unconventional way using these functions, but it gives you exactly the same class of joint distributions. And actually any directed graphical model can be written as a functional causal model or a structural causal model. Only it's not a unique way. So usually you have multiple structural causal models that lead to the same graphical model. Okay, let's move to the next slide. So I already said it entails a joint distribution, the observational distribution, and there's some interesting questions now about this. First one is, what can we say about distribution? I already told you a little bit about this informally. And the second thing is, can we recover the graph, or maybe even the graph and the functions, from observing this joint distribution? Next slide. And there's a beautiful theory about this, which was developed by people like Pearl and Stefan Lauritsen in Denmark, and others. And this is sort of the main summary of their results. This theorem, which says that these following four conditions are equivalent. First of all, the existence of a structural causal model. So in my case, I started with a structural causal model, which in a way is the most physical way of thinking of things, where each variable is just a function of other variables. So the functions directly represent the mechanisms that generate dependencies. The second equivalent condition is the so-called local causal Markov condition. And this condition says that it turns out that the entailed distribution, the observation distribution in this case, has a very particular statistical independent structure. Locally at each node, the variable is statistically independent of its non-descendants given the parents. Maybe we can briefly go back one slide. If we consider this variable here, the green one, the parents are the red things. So these are descendants, the white nodes. And by non-descendants, we mean everything that's not a descendant and not a parent. So the blue things. So X is independent. The local Markov condition says that X is the green thing is independent of the blue things when conditioned on the red things. So the red things shielded from the blue things, which in the graph kind of makes sense. Please move to the next slide again. So that's the local condition. And it turns out this local set of conditional independencies immediately implies a global set of conditional independencies. And that's something that requires the notion of deseparation, which I think I'll tell you about later in this tutorial. It's a graph theoretic notion. So this is it just turns out that these independencies immediately imply a larger set of independencies that are sometimes useful. And then finally, also equivalent is a factorization, and it's a factorization of the joint distribution here into a set of conditionals. And now what's interesting about these conditionals, so I told you at the beginning, I showed you the chain rule of probability theory. You can always factorize a joint distribution. And in this case, I was just taking any arbitrary ordering of the random variables, and then I just always write the first one. I write the overall thing as a conditional of the first n minus 1, etc. So I can always do that. But this decomposition is special in that here each node is conditioned only on its parents in the graph. So these are if the graph is not fully connected, or if the graph is relatively sparsely connected, these are much lower dimensional objects because these are just conditioned on a few parents here. And these things now here, that's another way of thinking of the physical mechanisms that generate dependencies. These things are called the causal conditions. So these depend on the functions sitting here in the node and on the noise variable of that node. And so these are in the structural equation view, it's maybe more explicit. You have both the function and the noise variable. And the noise variable sort of makes it a non-deterministic thing. And if you want, a conditional is nothing but a noisy function, right? Which that maps the input to the output with some noise. So these are called the causal conditionals. They are also sometimes called the causal Markov kernels. And it's important. So only those conditions are called causal that are of this form. So a variable conditioned on its parents. Sorry, conditioned on its causal parents. Okay, so if you just take any other arbitrary decomposition of this factorization, you will probably not end up with causal conditionals or with mechanisms. Let's move one slide on. Okay, so now people have thought, this is just briefly, people have thought a lot about this problem of structure inference or causal discovery. So given the distribution, given the observational distribution, which is entailed by the structural equation model, so by the noise variables and by the graph, given this distribution, can we say something about the graph? And the answer is, so we know that the graph structure implies certain conditional independencies of the joint distribution. So what we could try and do is we could test conditional independencies and infer which graph structures are consistent with that. And intuitively, this amounts to saying, well, we have these noise probes, we feed in independent noise at each node, and then we let the noise spread, and then we ask conditional questions of the form of, like, what does this node know about this one that it doesn't already know from this one, etc. So these kind of triplets we can ask. And that's intuitively, that makes sense. There's one detail, which is that the Markov condition that I showed you about before, it gives us an implication in this direction. So it says, if certain graph properties hold true, so for instance, so the local Markov condition said this green thing is independent of the blue things, given the red things. So if a certain graph property holds true, then a certain independence, statistical independence holds true. But if we do now the inference, we want to test for statistical conditional independence properties. So we want to start from this side and infer something about graph properties. So we really need the implication in the opposite direction. And what people have done is they have basically added this as an assumption and called it faithfulness. So that sounds a little bit ad hoc, but people have argued that this is kind of the probability of this happening by chance, it requires different paths cancelling each other, etc. Maybe we'll get back to that later. So it's kind of plausible to say and assume, let's assume this is actually not an implication, but an equivalence. So we'll assume the backward direction is also true. Yes, there are some issues about that, but I won't go into this now. So let's move to the next slide. Okay, so now we get to the notion of intervention. So the beautiful thing about a structural causal model is not only does it give you the whole world of standard probability and standard graphical model, but it also lets you talk about interventions in a system and about shifts in a system. So it talks about all sorts of interesting things that standard machine learning has trouble with. And an intervention is actually trivial in this case. Intervention simply means take one of the structural assignments, so structural equations, something it's called a structural equation model. The annoying thing is they're not really equations because, and that's why I usually try to write it as an assignment, like in computer science, because the left and the right are different. There's a physical mechanism that takes this as inputs and produces this as an output, and you can't just rearrange these equations. If you rearrange them, then they are no longer structural, or they no longer have a physical meaning. But anyway, if you take one of these assignments and you replace it with another one, for instance, with the trivial one that simply sets this variable to a constant that you choose. So that's a form of an intervention in a system. You just clamp one variable to some value. So now let's say you do this for x, you clamp this to a certain value. That means you just have another structural equation model now, where one equation has been changed. You can do the same thing as before. You can still compute what is the entailed distribution of all variables. You get a different distribution. It's no longer the observational distribution, but this one will be called an interventional distribution that corresponds to this intervention here. And so there's various things that are contained as special cases. Okay, so let's move to the next slide. So now we can think again a little bit about this principle of independent mechanisms, using the things that we've learned since then. We think of the causal decomposition of the structural equation model, or of the overall graph, or the overall distribution, I should say. It looks like this. And a precondition for interventions to make sense. So intervention means you are changing one of these assignments, or in other words, changing one of the causal conditionals. And of course, for this to make sense, you have to assume that this is possible, so that you can locally change one of these things. So that means this requires that the other ones, as you change one of them, the other ones are unaffected. So this possibility of making a localized intervention already presupposes that there is some form of independence between these components. That's maybe trivial, but I think it's worth pointing out that, and I think I won't go through this in detail now, but let me move to the next slide to give you an example where I think one can argue that our own inference systems make use of similar kinds of independence assumptions all the time. And this is an example from vision. This object here in the background is called a Boucher chair. As you can see, it's not a chair, it's two objects. And whenever we look at an object, I think we implicitly, or our brain implicitly, makes the assumption that the object out there in the world and our process of perception are independent. And this means, in particular, the line of sight is independent from the object. And if we violate this assumption, then perception goes wrong. If we look through this hole, please go to the next slide, then you see an object which is not there in reality. So perception fails if our perceptual process is tuned to the object. So if the object, the input, and the mechanisms by which we process the input into our percept are dependent, then perception fails. And this is I think this is a general principle, or this makes it plausible that we actually use this kind of assumption. And we do it all the time. There's also this thing in computer vision which is called structure from motion. So you can take a 3D object, and even if you close your eyes, you don't have stereo vision. If you move around your head about the object, you get an idea of the three-dimensional structure of this object. And this implicitly has to assume that as I move around, so I change the mechanism by which I turn this object into a percept, I have to implicitly assume as I move around, the object itself does not change. Otherwise, I can fool my system in arbitrary ways. The fact that we can do this kind of 3D perception by moving our heads shows that we are implicitly making this kind of assumption. Okay, let's move to the next slide. Yeah, so one way to write this independent mechanisms assumption is just to say that the causal generative process overall, the causal generative process is composed of autonomous modules. So one is in this case, one is the object out there in the world. The other module is our perception that do not inform or influence each other. And as I just mentioned in the case of structural motion, it also has this interpretation in terms of invariance. As one of the modules changes, by default, we would assume the other one to be invariant. Okay, next slide. I have a nice video if this plays. This is from the National Gallery in London. You see this strange object down here in an image. This is the image of Hans Holbein the Younger. And as you move to the side, it becomes a skull. So it's also a place with this kind of independence. So this is the one dependent viewing direction. Yeah, let's move to the next slide. So I should also, I'm not going to go through all this in detail, but just briefly point out, a course on causality wouldn't be complete without mentioning the notion of counterfactuals. This was first formalized by Jerzy Neyman, and now there's a large class of models in causality, which is the Neyman-Rubin model. And for Neyman, the study of causality started with a problem from agriculture. I think he was a Polish statistician, where you imagine you have m plots of land, and then you have new varieties of crop. And on each plot of land, you can plant one crop. So the problem is on each plot of land, you can't test multiple types of crop at the same time. But at the end, you really would want to know for each plot of land how much crop yield you would have observed if you had planted the variety I on that piece of land. So there's this whole matrix of what would have happened if you had planted something on the piece of land. But unfortunately, from this matrix, in each row we can only, or in each column, we can only measure one of the actual quantities. And all the other ones are called counterfactuals, because we haven't actually measured them. We can hypothetically think about them, and causality would really like to say something about those. And from this point of view, you can view of this simple, I mean, it doesn't have all the complicated graph structure, etc. It's one simple setting. In this case, you can think of causal inference as a missing data problem, and there's this framework due to Neyman and Rubin, which is called the potential outcomes framework. Let's move to the next slide. Actually, I think I'm going to actually skip this and instead move one slide further. So people often ask, why do you talk about causality? So far I didn't mention the notion of time, and somehow we all think causality must have something to do with time. And of course it does have something to do with time, and I'll also get back to this later again. I want to take this one point further. If you move one slide further, I would even say, so if you question whether we can talk about causality without mentioning time, you're effectively questioning even whether we can talk about statistics without mentioning time. because in the end, from my point of view, so first of all, follow Reichenbach, all statistical dependencies are due to causal dependencies. And in the end, all causal dependencies are due to physical mechanisms acting in the real world. So for instance, if I take, I think many of you will have worked with the MNIST data set. If you think about why can we do machine learning based on the MNIST data set? So it's a data set of handwritten digits, and each digit is labeled with some class membership. You think about so we can do something with this data set because there's a statistical dependence between the appearance of the digit and the class membership. Our algorithms exploit this statistical dependence, but where does the statistical dependence come from? These digits were written by humans. I don't know, maybe they were writing zip codes on envelopes or something like that. So some human in their head decides, I want to produce the image of a digit 7. A complicated motor program starts. We don't understand all the details, but somehow this person then produces an image that looks like a 7. So it's a highly maybe in principle, maybe we could model all the physics once we understand the brain, the dynamics of the arm, etc. We could model the physical process that generates this statistical dependence, but it's not really realistic, certainly not at this time. But what we can do, it turns out, for this particular dynamic process that leads to handwritten digits, it turns out that the end result carries this nice, simple statistical dependence that we can then use for machine learning. And the same, so this is true in all of statistics. I think in the end, I think all dependencies are due to time evolutions involving multiple variables. This is true for causal structures, it's true for statistical structures. Of course, it is true also in time-dependent settings. The standard IID setting that we like to deal with in machine learning is just a particularly simple setting where we don't have to care too much about the dynamics. And the same holds true for some causal problems. Not all causal problems can be discussed without talking about time. And not all dependencies in the world can be understood without talking about time. But there are some, and we're getting a lot of mileage out of those. But we should never forget that the world is more complicated. Okay, so let's move to the next slide, which is still also talking about this point to some extent. So if we think about an overall taxonomy of models or of ways we can model the world, then you could say there's so all the way down here is the statistical model. That's what we usually do. A statistical model allows us to make predictions as long as we're in an IID setting, so independent, identically distributed data. Statistical model doesn't allow us, at least not without additional assumptions, to make predictions when distributions change or when there are interventions. It doesn't allow us to answer counterfactual questions. It doesn't necessarily give us physical insight. But the great thing about a statistical model is it can be automatically learned from data. So that's the big strength. That's why we do this most of the time. Now, on the other extreme is a mechanistic model. So if we're physicists and we really try to understand a system in great detail, in principle, I think from a mechanistic model, you can do everything. You could make predictions. You can even understand what changes in some other variables change. You can answer counterfactual questions. You get insight. But probably, at least currently, you can't automatically learn them from data. It requires intelligent physicists. It requires a series of experimentation, etc. And then there's this world in between, and that's what causality tries to cover. And basically, what we're trying to do is we try to retain this nice property that things can be learned from data, but get stronger on some of these points that statistical models do poorly on. So we try to predict also when distributions change or when there are interventions, etc. And maybe also get more insight. That's also debatable. So I think causality also has something to say about interpretability. So if you go to the next slide, so sometimes So we've analyzed one setting where you start with a mechanistic model and then you derive a structurally causal model. Please, next slide. From it, I'm not going to talk about that, but so this is just one example where we start with a coupled set of differential equations, and then, yeah, I think you just lost it, but I can say one more sentence about this. So you start with a set of differential equations, and then you consider equilibrium states of these equations. So in equilibrium states, you have the variables that appear in the differential equation. They are related to each other in certain ways in equilibrium states, and now you can try to perturb these equilibrium states a little bit and see how they adjust, and by this construct a causal graph of how in the equilibrium state the variables are related to each other. And that means in the end you derive a structural equation model that provides a very simplified account of the causal structure given by the complex set of differential equations that only describes how this overall system responds to small perturbations in equilibrium states. And already this gives you a complex causal model. And of course the full dynamic model is much, much richer than this. But it's interesting to try to connect these different worlds to each other. So let me see, where do I continue? So now I have, actually I think I'm already, if you press the button like 3 or 4 times, keep going. So that's exactly where I wanted to arrive now. Thank you very much.